The equations are not broken. They have been checked for 100 years and they keep passing every test. That is the problem, because if the math is right, the future already exists. The universe could end before you finish this sentence. You may have already died 1,000 times. And the odds say your memories were never real. 10 paradoxes. Not science fiction, published physics, written by people who wanted them to be wrong. Let's count them down. Number 10. The Andromeda Paradox. Stand still and look toward the Andromeda galaxy, 2.5 million light-years away. Somewhere in your right now, something is happening there. Now take a step toward it. Your right now on Andromeda just jumped forward by about a day. Step away and it jumps back. Walk to your mailbox, and entire days of Andromeda's history slide in and out of your present, decided by nothing but the direction of your feet. This is not a trick. It falls straight out of Einstein's special relativity. Observers moving differently slice spacetime into different nows, and across millions of light-years, even walking speed shifts the slice by days. Philosopher Hilary Putnam ran the logic in 1967. Roger Penrose sharpened it into the Andromeda Paradox. Here is why it matters. Suppose a fleet on Andromeda is deciding, right now, whether to launch. For the version of you standing still, the decision hasn't happened yet. For the version of you walking forward, it already has. Both of you are correct, which means the undecided future of one observer is the already fixed past of another. Follow that to the end and you get the block universe. Past, present, and future all equally real, all already there. Your birth, this moment, your death. All of it sitting in the block, like frames of a film that was finished before it was played. You are not moving through time. You are just the frame that happens to be lit. Number 9. The Fermi Paradox. The Milky Way is over 13 billion years old. It holds somewhere between 100 and 400 billion stars. In 2013, astronomers used Kepler telescope data to estimate that billions of those stars have Earth-sized planets in the habitable zone. The universe has been running this experiment billions of times for almost all of time. So where is everyone? In 1950, physicist Enrico Fermi asked exactly that over lunch, and the question never went away. A civilization only slightly older than ours, thousands of years, not millions, could spread across the entire galaxy in a few tens of millions of years, even at a small fraction of light speed. On cosmic clocks, that is nothing. The galaxy should already be full. The sky should be loud. It is silent. Scientists have tried every escape. They're hiding. They went digital and stopped expanding. They destroy themselves first. Interstellar travel is harder than we think. Every explanation works a little. None of them work completely. Which leaves the explanation economist Robin Hanson wrote down in the 1990s, the Great Filter. Somewhere on the road from dead chemistry to a galaxy-spanning civilization, there is a step that almost nothing survives. If the filter is behind us, we are the rarest thing that has ever happened. If it is ahead of us, then the silence is an emptiness. It's a warning. Every dead planet out there took the same next step we're about to take. Number 8. False vacuum decay. Empty space is not nothing. It has an energy level, a setting, and everything in physics prefers the lowest setting it can reach. A ball rolls to the bottom of the hill. A universe should too. Here is the problem. When physicists measured the mass of the Higgs boson in 2012, the numbers landed in an uncomfortable place. Run them through the equations, and our vacuum doesn't look like the bottom of the hill. It looks like a ledge, a resting point partway down, a false vacuum, and a false vacuum doesn't have to stay put. Physicist Sidney Coleman worked out the math in 1977. Quantum mechanics allows a tiny bubble of true vacuum, real bottom-of-the-hill space, to appear anywhere, at any moment, at random. Inside that bubble, the constants of nature are different. Chemistry doesn't work. Atoms don't hold. Once the bubble forms, it expands at essentially the speed of light, converting everything it touches. You cannot see it coming. The wall arrives with the light that would have warned you. There is no alarm, no flash, no final broadcast. One instant the universe is here. The next instant, at one random point, it isn't, and the edge of that instant is racing toward everything else. The calculations say the odds of it happening near us anytime soon are absurdly small. Trillions upon trillions of years. Probably. But probably is the honest word. Right now, the vacuum you are sitting in may already have failed, somewhere out there, and the bill is on its way. Number 7. The measurement problem. Fire single electrons at a barrier with 2 slits and watch nothing. Each electron passes through both slits at once, interferes with itself, and builds a wave pattern on the far wall. Do the same experiment while checking which slit each electron used, and the pattern vanishes. The electron becomes a particle. It picks one path, because you looked. This is not philosophy. It is one of the most repeated results in the history of science. It has been done with electrons, with atoms, and in 2019 with molecules of 2,000 atoms, objects big enough to border on biology. It gets worse. In 1978, physicist John Wheeler proposed a version where the decision to look is made after the particle is already in flight. It was actually performed in 2007. The result: the choice you make now still determines how the particle behaved back then. As if the present quietly edits the past. So what counts as looking? A detector? A computer? A mind? 100 years in, physics has no agreed answer, only camps. Copenhagen says the wave collapses when measured and declines to define measured. Many worlds says it never collapses. Every outcome happens, and there are countless versions of you. Pilot wave theory says the randomness is fake and everything was decided in advance. They all match every experiment ever run. They describe completely different realities. Strip away the jargon, and the situation is this. We do not know what happens when you look at the universe. And the universe has spent 13 billion years mostly unlooked at. Number 6. The arrow of time. You remember yesterday and not tomorrow. Eggs break and never unbreak. Causes come before effects. Nothing in your life is more obvious than the direction of time. Now open the equations, Newton's laws, Maxwell's electromagnetism, Einstein's relativity, Schrödinger's quantum mechanics. Run any of them backward, and they work exactly as well as forward. The fundamental laws of physics do not contain an arrow of time. Film 2 billiard balls colliding, play it in reverse, and physics approves of both versions. The one exception is not really a law. The second law of thermodynamics, entropy increases, disorder grows, is statistics. It says disorder is overwhelmingly more likely, not mandatory. Ludwig Boltzmann proved it in the 1870s by counting arrangements. There are astronomically more ways to be scrambled than sorted. A broken egg can reassemble. The odds are just so small the universe hasn't waited long enough. Here is the crisis. If the laws are directionless and entropy is just probability, then time's arrow isn't fundamental. It exists only because the universe began in an absurdly ordered, low-entropy state at the Big Bang, and we are still riding the slide downhill from it. Physicists call this the past hypothesis. Nobody knows why the beginning was so ordered, which means the flow of time, memory, cause, the difference between birth and death, is not a law of nature. It is a leftover, the afterglow of a 14-billion-year-old accident. And in a universe that runs long enough, the slide ends, and forward stops meaning anything at all. Number 5. The fine-tuning problem. The universe runs on a couple dozen numbers: the strength of gravity, the mass of the electron, the energy of empty space. They do not come from any equation we know. They are simply set. Astronomer Royal Martin Rees calls them the recipe of the cosmos. And the recipe is terrifyingly precise. The worst case is the energy of empty space, the cosmological constant. Quantum theory, calculated naively, predicts a value up to 10 to the power of 120 times larger than what we measure. That is a 1 followed by 120 zeros. Physicist Steven Weinberg called it the worst prediction in the history of physics. If the real value were even slightly bigger, space would have expanded too fast for galaxies, stars, or planets to ever form. Nudge other constants, and atoms never bind, stars never ignite, chemistry never happens. We won a lottery whose odds have no name, so scientists tried to escape. Answer 1. There is a deeper law that forces these values, a law nobody has found in a century of looking. Answer 2. The multiverse, endless universes with random settings, and we are simply in one of the rare ones where observers can exist to ask the question. Untestable, maybe forever. Answer 3 is the one physics has spent 300 years trying not to need. Pick whichever unsettles you least. There is no fourth option on the table. The dials were set before the first second of time. Nobody knows whose hand was on them. Number 4. The simulation argument. In 2003, Oxford philosopher Nick Bostrom published a paper that has never been refuted, only argued with. It says at least one of 3 things must be true. 1. Civilizations go extinct before they can build planet-scale simulations of minds. 2. They can, but none of them ever choose to. 3. Simulated minds vastly outnumber real ones, and you are almost certainly one of them. The logic is brutal arithmetic. A mature civilization's computers could run billions of simulated histories, billions of simulated minds for every biological one. If that ever happens, once, anywhere, then a randomly chosen conscious being is overwhelmingly likely to be inside the machine. You are a randomly chosen conscious being. Physicists have looked for fingerprints. In 2012, researchers pointed out that simulating physics on a grid would leave artifacts, including a hard ceiling on the energy of cosmic rays. Our universe has exactly such a ceiling. It also has a perfectly natural explanation for it. That is the trap. A good simulation and a real universe may be impossible to tell apart from the inside. Here is the part that keeps people awake. If this is a simulation, the laws of physics are not laws. They are settings. The speed of light is a frame rate. Death is a subroutine. And somewhere outside the machine, something can pause it, rewind it, or switch it off, and no experiment we run in here will ever reach them. You cannot falsify it. You cannot escape it. You can only decide not to think about it, which is what you'll do in about 90 seconds. Number 3, quantum immortality. The many-worlds interpretation of quantum mechanics, proposed by Hugh Everett in 1957, says the universe never chooses. Every quantum event that can go 2 ways goes both ways, and reality branches. Both outcomes happen. Both are real. This is a mainstream position. A sizable share of working physicists take it seriously. In 1997, physicist Max Tegmark noticed what it implies and built a nightmare to prove it. A device wired to a quantum coin flip. 50-50, decided by a single particle. The experiment only works if you are the one in the chair. The branches split. In one, it ends. In the other, the device just clicks. But here is the trick. There is no version of you that experiences the ending. The only branches containing your experience are the ones where the device failed. Run it 10 times, 100 times. From the inside, you hear 100 clicks. From the inside, you cannot lose. Follow the logic all the way and it whispers something enormous. Subjectively, you always find yourself in a branch where you survived. Every close call you have ever had, you may simply be the copy that made it. Tegmark himself pumps the brakes. Real death is not a clean quantum coin flip. It is gradual and messy, and the argument may not transfer. But the core logic has never been refuted, only declared too disturbing to use. And it has a shadow. The mathematics protects only the observer. Everyone you love keeps dying in branches you are still inside. Many worlds means never having to say goodbye to yourself. Number 2, the Bootstrap Paradox. A time traveler visits Beethoven, carrying the printed score of the Fifth Symphony. Beethoven, it turns out, never wrote it. He copies the score, publishes it, becomes immortal. Centuries later, the time traveler photocopies that score, goes back, and hands it over. Now answer one question. Who composed the Fifth Symphony? Not Beethoven, he copied it. Not the traveler, they copied it too. The music exists in a closed loop with no author, no origin, no first draft. It was never created. It is simply there. Here is what makes this physics instead of fiction. In 1949, Kurt Gödel, Einstein's closest friend at Princeton, found solutions to Einstein's own equations containing closed time-like curves, paths through spacetime that loop into their own past. Einstein was disturbed. The equations were not. And when physicists in the early 1990s, following Igor Novikov, analyzed objects sent around such loops, they found the universe doesn't forbid them. It only demands consistency. The loop must agree with itself. That is the single rule. An uncaused symphony breaks no equation, which quietly detonates something we believed was bedrock, that every effect has a cause, that every chain of events traces back to a beginning. If closed loops are possible, there can be information in the universe with no source at all. And here is the last turn of the screw. We are inside the universe. If some piece of our history is a loop, there is no experiment, even in principle, that could tell us. Number 1, the Boltzmann Brain. Everything you know rests on one assumption, that your memories happened. Here is the paradox that says the odds are against it. In the 1890s, Ludwig Boltzmann, the same man who tamed entropy, faced a question. If disorder always wins, why do we see an ordered universe at all? His answer: given infinite time, random fluctuations will occasionally assemble order out of chaos. Wait long enough, and atoms will accidentally arrange themselves into anything. 21st century cosmologists did the accounting and found the monster in it. A fluctuation that produces an entire universe, 100 billion ordered galaxies, is unimaginably rarer than a fluctuation that produces one single brain. A brain floating in the void, complete with false memories of a childhood, a career, a family, and a video it believes it is watching right now. Run the numbers in an eternal universe, and the conclusion is unavoidable. Random observers should outnumber real ones by a margin with no name. If you are a typical observer, you are not the real thing. You are the fluctuation. Your past never happened. Your world is 1 second old, and it will not last 2. Cosmologists like Sean Carroll treat this as a 5-alarm fire in our theories, precisely because it cannot quite be ruled out. Any argument you build against it uses memories, and reasoning the paradox says you cannot trust. The math refuses to save you. You feel real. You remember this video starting. A Boltzmann brain would feel exactly the same. And physics cannot yet explain why you should believe you are anything more. 10 paradoxes, 0 comfortable answers. The future may already exist. The vacuum may already be falling. And the equations, the same ones that build your phone and fly our probes, cannot promise that you existed 10 seconds ago. The universe did not hand us answers. It handed us questions with teeth, and every time physics gets sharper, they bite deeper. Sleep well, in the branches where you can. If your brain survived this one, the next video will finish the job. It's on your screen now.